Let's suppose that we've carried out the observational study of smoking cessation methods. We're trying to determine which method works best: drugs to alleviate nicotine addiction, therapy, combined drugs and therapy, or simply quitting. The explanatory variable is the method, while the response variable is eventual success or failure in quitting. Our study shows that the percentage succeeding with the combination drug and therapy method was highest, while the percentage succeeding with neither therapy nor drugs was lowest. In this example, there is clear evidence of an association between method used and success rate. Can we conclude that the combination drug therapy method causes success more than using neither therapy or drugs?
It is at precisely this point that we confront the underlying weakness of most observational studies. Some members of the sample have opted for certain values of the explanatory variable, method of quitting, while others have opted for other values. It could be that those individuals may be different in additional ways that would also play a role in the response of interest. For instance, suppose older people are more likely to choose certain methods to quit, and suppose older people in general tend to be more successful in quitting than younger people. The data would make it appear that the method itself was responsible for success, whereas in truth, it may just be that being older is the reason for success. We can express this scenario in terms of the key variables involved.
In addition to the explanatory variable, or method, and the response variable, success or failure, a third lurking variable, age, is tied in or confounded with the explanatory variable's values and may itself cause the response to be success or failure. We could control for the lurking variable age by studying older and younger adults separately. Then, if both older and younger adults who chose one method have higher success rates than those opting for another method, we would be closer to producing evidence of causation. The diagram demonstrates how straightforward it is to control for the lurking variable age by modifying your study design. Notice that we did not claim that controlling for age would allow us to make a definite claim of causation, only that we would be closer to establishing a causal connection. This is due to the fact that other lurking variables may also be involved, such as the level of the participant's desire to quit. Specifically, those who have chosen to use the drug therapy method may already be the ones who are most determined to succeed, while those who have chosen to quit without investing in drugs or therapy may, from the outset, be less committed to quitting.
To attempt to control for this lurking variable, we could interview the individuals at the outset in order to rate their desire to quit on a scale from 1 to 5, with 1 being the weakest and 5 being the strongest. Then we could study the relationship between method and success separately for each of the 5 groups. But desire to quit is a very subjective thing, difficult to assign a specific number to. Realistically, we may be unable to effectively control for the lurking variable, desire to quit.
Who's to say that age and/or desire to quit are the only lurking variables involved?
There may be other subtle differences among individuals who choose one of the 4 various methods to quit smoking. And researchers may fail to conceive of these subtle differences as they attempt to control for possible lurking variables. For example, smokers who opt to quit using neither therapy nor drugs may tend to be in a lower income bracket than those who opt for drugs and/or therapy, because they can afford this method. Perhaps smokers in a lower income bracket also tend to be less successful in quitting because more of their family members and co-workers smoke. Thus, socioeconomic status is yet another possible lurking variable in the relationship between cessation method and success rate.
It's because of the existence of a virtually unlimited number of potential lurking variables that we could never be 100% certain of a claim of causation based on an observational study. Observational studies cannot prove causality. On the other hand, observational studies are an extremely common tool used by researchers to attempt to draw conclusions about causal connections. To do this, great care must be taken to control for the most likely lurking variables. Only then can researchers assert that an observational study may suggest a causal relationship.
So far, we've discussed different ways in which data can be used to explore the relationship or association between two variables. When we explore the relationship between two variables, there is often a temptation to conclude from the observed association that changes in the explanatory variable cause changes in the response variable. In other words, you might be tempted to interpret the observed association as causation. The purpose of this part of the course is to convince you that this kind of interpretation is often wrong. The motto of this section is one of the most fundamental principles of this course. Association does not imply causation.
For example, house fires and wildfires cause substantial damage when they occur. What variables might affect the extent of this damage? This scatter plot illustrates how the number of firefighters sent to fires on the x-axis is related to the amount of damage caused by fires on the y-axis in a certain city. The scatter plot clearly displays a fairly strong or slightly curved positive relationship between the two variables. Would it then be reasonable to conclude that sending more firefighters to a fire causes more damage, or that the city should send fewer firefighters to a fire in order to decrease the amount of damage done by the fire? Of course not. So what's going on here? There is a third variable in the background, the seriousness of the fire, that's responsible for the observed relationship. More serious fires require more firefighters and also cause more damage. This model will help you visualize this situation. The seriousness of the fire is a confounding variable. In statistics, a confounding variable, also known as confounding factor, a lurking variable, a confound or confounder, is an extraneous variable that is associated positively or negatively with both the explanatory variable and response variable. We need to control for these factors to avoid incorrectly believing that the response variable is associated with the explanatory variable.
Confounding is a major threat to the validity of inferences made about the statistical associations. In the case of a confounding variable, the observed association with the response variable should be attributed to the confounder rather than the explanatory variable. In science, we test for confounders by including these third variables, or fourth or fifth or sixth, in our statistical models that may explain the association of interest. In other words, we want to demonstrate that our association of interest is significant even after controlling for potential confounders.
Because adding potential confounding variables to our statistical model can help us to gain a deeper understanding of the relationship between variables, or lead us to rethink an association, it's important to learn about statistical tools that will allow us to examine multiple variables simultaneously. That is, look at more than 2 or 3 variables at the same time. The general purpose of multivariate modeling techniques, such as multiple regression and logistic regression, is to learn more about the relationship between several explanatory variables and one response variable.
These regression procedures are very widely used in research. In general, they allow us to ask and hopefully answer the question, what is the best predictor of, and does variable A or variable B confound the relationship between my explanatory variable of interest and my response variable?
For example, educational researchers might want to learn about the best predictors of success in high school. Sociologists may want to find out which of the multiple social indicators best predict whether or not a new immigrant group will adapt to their new country of residence. Biologists may want to find out which factors, such as temperature or barometric pressure or humidity, best predict caterpillar reproduction. So how can multivariate models help us to evaluate the presence or absence of confounding or lurking variables? Since the difficulty arises because of the lurking variable's values being tied in with those of the explanatory variable, one way to attempt to unravel the true nature of the relationship between explanatory and response variables is to separate out the effects of the lurking variable.
You may have already identified a significant relationship between your explanatory and response variables, and now want to think about whether this is a real relationship, or if instead the relationship is confounded by one or more lurking variables.
For example, here's a graphical association between birth order and number of cases of Down syndrome per 100,000 live births. As you can see, it looks like a linear association where the firstborn in a family has the lowest likelihood of having Down syndrome. With later birth order, up to a fifth-born child, there's increased risk of being born with Down syndrome. This is a statistically significant association when analyzed via a chi-square test of independence, with birth order as the categorical explanatory variable and the presence or absence of Down syndrome as the two-level categorical response variable. Another statistically significant relationship is the association between maternal age at a child's birth and the likelihood that the child will have Down syndrome. You can see here that babies of younger women, up to about the age of 29 or 30 to 34, have really low rates of Down syndrome. Among mothers aged 35 to 39 and older, you see the rates are clearly higher.
Remember, in the case of a confounding variable, the observed association with the response variable should be attributed to the confounder rather than the explanatory variable. We test for confounders by including these third variables, or fourth or fifth, in our statistical models that may explain the association of interest.
In these examples, it's possible that the association between a child's birth order and risk for Down syndrome could be confounded by maternal age. Alternately, the association between maternal age and Down syndrome might be confounded by birth order. Or, both birth order and maternal age might independently predict the likelihood of a diagnosis of Down syndrome after controlling for each other. Here's a graph that answers this question by showing that maternal age confounds the relationship between birth rank and Down syndrome, and that it's really maternal age rather than birth rank that's associated with Down syndrome. Here you see birth order along the horizontal axis. The maternal age groups are along the z-axis. Then on the y-axis, we have cases of Down syndrome per 100,000 live births. If we look across birth order separately for each maternal age group, we see that there really is no difference in rates of Down syndrome by birth order. In other words, once we control for the age of the mother, that is, examine the rates of Down syndrome across birth order, but one maternal age group at a time, there's no association between birth order and Down syndrome. If we look at rates of Down syndrome across maternal age for each individual birth order, we see an upward trend as maternal age increases. So if you look across these colors, this is a great graphical representation where we see that it isn't birth order that is associated with Down syndrome, it's maternal age. In other words, once we control for birth order, there's still an association between maternal age and Down syndrome. Birth order does not confound the relationship between maternal age and Down syndrome. The relationship holds even after controlling for birth order.
Here is another question about confounding. I start with a simple question about an association between an explanatory and response variable. Is the incidence of coronary heart disease greater among men who drink coffee than among men who don't drink coffee? My response variable is coronary heart disease, and my explanatory variable is a history of coffee drinking. If I find a significant association in my data, I will also want to evaluate whether there are other variables that might confound or explain the relationship. It strikes me that some people who drink lots of coffee do so while also smoking cigarettes. So I would like to evaluate if smoking is a confounder in the relationship between coffee drinking and coronary heart disease.
This relationship between coffee drinking and coronary heart disease is the one that we're testing. But we also want to partial out or remove smoking from that association. We want to see if that relationship between coffee drinking and coronary heart disease is still significant after we account for smoking. Here's a Venn diagram that illustrates how our multivariate models will handle this question. Coronary heart disease is our response variable. Our explanatory variable is coffee drinking. Our basic question is, do we know something about the presence or absence of coronary heart disease by knowing the level of coffee drinking in our sample? But we may also know or believe that smoking is related to both coronary heart disease and coffee drinking. So we want to include smoking in our model as a possible confounder in the relationship between coffee drinking and coronary heart disease. Other terms used to describe potentially confounding variable in my statistical model include control variable, covariate, third variable, or lurking variable. When we're looking at the association between coffee drinking and coronary heart disease, the overlap you see in the Venn diagram is what we're testing. We're saying, is that overlap significant? Are they significantly associated? When we add the potential confounder of smoking, we're asking, is coffee drinking and coronary heart disease still significantly associated after we partial out the overlap between coffee drinking and coronary heart disease that can be accounted for by smoking? Because smoking is associated with coronary heart disease and coffee, there's a part of the association between coffee drinking and coronary heart disease that can be accounted for by smoking, the highlighted area in the Venn diagram. What we want to do is mathematically partial that out. When we run multivariate models, we're partialing out the portion of the association between the explanatory and response variables that can be accounted for by that overlap with the third variable.
For this course, we will only be discussing two types of multivariate models: the multiple regression, where our response variable is quantitative, and the logistic regression, where our response variable is binary.
That is a two-level categorical variable.
The question of when is a third or fourth or fifth variable in our multivariate model a confounder is strategically important. If the variable is a confounder when we include it in the statistical model and the association of interest is no longer statistically significant, then we can determine that our original variables had no real relationship. Testing for confounding variables with multivariate models is vital in the testing for true statistically significant associations or real relationships between variables in our research.
If we had run the model with maternal age and birth order predicting Down syndrome, birth order would have been significantly associated with Down syndrome in that first model. Once we added maternal age to the model as a potential confounder, the association between birth order and Down syndrome would no longer be significant.
So we now know that we will use multiple regression to evaluate multiple explanatory variables and/or potential confounders when predicting a quantitative response variable. So how does a linear regression analysis work? Let's start with a simple example.
We imposed our causal model on observational data by selecting our explanatory and response variables denoted by x and y and placed on the x and y axis of a bivariate graph. Let's return to the graph that we made earlier using the Gapminder dataset. Here, we visualize the association between internet use rate in a country and the percent of its population that lives in an urban setting. As you'll recall, we place the explanatory variable on the x-axis and the response variable on the y-axis. So our research question is the rate of urbanization associated with the rate of people who use the internet? As you can see, we also ran a Pearson correlation and found a pretty strong, positive, and significant linear association between these two variables. R equals 0.61. In order to test this model, our first goal is to determine the equation of that best fit line, the line that we created in our graph that shows the best linear fit between our two variables of interest. As you may recall from high school algebra, the equation of a line is usually defined as y equals mx plus b, where x and y are the variables that are on those respective axes. M is the slope of the line, and b is the y-intercept, the spot where the line crosses the y-axis. In our model, we know that internet use rate is our y, or response variable, and urban rate is our x, or explanatory variable. So we need to determine our slope and our intercept in order to define this best fitting line. In statistics, we often use terminology that's a little different from y equals mx plus b. Our symbols y and x remain the same, but we call the slope of variable x the beta sub 1 value, and the intercept of our model is called our beta sub 0 value. These beta values are often called coefficients. Together, beta sub 0 and beta sub 1 times x make up what is called the linear component of our model. In addition, we will always have some error in our data, and so we must include that in our model as well. So how do we find the equation of this best fit line? In SAS, the procedure that we will be using is called PROC-GLM. GLM stands for General Linear Model. As you can see from the sample syntax, after the PROC-GLM semicolon, you use the word model followed by the response variable, equal sign, and then the explanatory variable, followed by a semicolon. For this sample research question from the Gapminder dataset, we'll type PROC-GLM semicolon model internet use rate, which is our response variable, equal to urban rate, which is our explanatory variable, followed, of course, by a semicolon. So let's run this program and look at the output. First, you can see the number of observations and number of observations with complete data that were used in the model. Here we see the name of our response variable. Next, let's move to the parameter estimates at the end of our output. Here we have our estimates, also known as coefficients or beta weights, for both our intercept and for the variable urban rate. Thus, the beta sub 1 value here is 0.72, and the beta sub 0 value is negative 4.90. So we now know that our equation for the best fit line of this graph is internet use rate equal to minus 4.90 plus 0.72 times urban rate. Before we analyze this equation a little more in depth, let's look at a few more components of our output. For example, we also have a column called PR greater than T, which gives us the p-value for explanatory variable's association with the response variable. This p-value will be the same one we get if we run a Pearson correlation on these two variables. The GLM procedure also gives an R-squared value, a value that we talked about in the chapter on Pearson correlation. Now, we don't need to calculate the R-squared value by hand, as it will be directly given to us. We know now that this model accounts for about 38% of the variability we see in our response variable, internet use rate. Let's return to the equation for the line that we generated. Look at how our equation is written. Y is a function of the variable x and some constant. Thus, as x changes, y will change with it. In building this model, we're saying that we believe that x relates to y in some meaningful way. What's exciting about this equation is that we can also use it to generate predicted values for y. The symbol that we use for predicted values of y is y hat. For example, let's say we're told that a country has 80% urbanization. Can we predict their level of internet use? Yes. We just plug the value 80 into our equation where we have our x value. As you can see, in a country with 80% urbanization, we would expect 52.7 people out of every 100 to use the internet. Also note from our beta sub 1 that this value is by how much internet use would increase for every 1 unit increase in urban rate. For example, if we had a country with 81% urbanization, we would know that we would expect their internet use rate to be 0.72 people higher, that is almost 1 person, than a country with 80% urbanization. However, note that this is only the expected internet use rate given what we know about urbanization. It's the value that rests exactly on the best fit line. Unless our data were perfectly correlated, we would anticipate that our expected value and our observed values would differ from one another to some extent. From our analysis, we now know that there's a statistically significant association between urban rate and internet use rate, and we can also tell you what we would expect internet use rate to be for a given country given its urban rate. This statistical model has opened the doors to being able to better understand what's really going on between internet use rate and urbanization. As long as we keep in mind that we're limited by the fact that we impose the causal model rather than being able to directly test for causation, and that expected data is not the same as observed data, we're still able to explain much about this relationship of interest.
For example, Canada has an urban rate of about 80%. However, its internet use rate is observed at 81.3, not 52.7. This is exactly why we include an error term in our model. We are not perfect diviners of the future. What we can do with statistics, however, is identify trends in our data and use those trends to look at what we would expect our data to look like. These trends are incredibly important.
This equation makes a lot of sense to us when we're working with a quantitative explanatory variable and quantitative response variable. But what about a categorical explanatory variable and quantitative response variable? It obviously wouldn't make very much sense, for example, for us to create a scatter plot and use gender as our predictor variable. However, a regression model will still be informative. Let's look at the output testing the linear relationship between depression and number of nicotine-dependent symptoms, where major depression is a binary categorical explanatory variable and number of nicotine-dependent symptoms, ranging from 0 to 7, is a quantitative response variable. Our research question is having major depression associated with an increased number of nicotine-dependent symptoms? In this code, the response variable comes first, then the explanatory variable. The full code is proc glm semicolon model nd symptoms equal to major dep life / solution, and it ends with a semicolon. The solution option is necessary in order to generate parameter estimates for the regression model. We also see the same output format as with the Gapminder regression example, with number of observations and number of observations with complete data that were used in the model, and the name of our response variable, and here are our parameter estimates and p-values. Thus we know that our equation is nd symptoms equal 2.19 plus 1.36 times major dep life.
Let's consider what this equation actually means, since it's not a best fit line of the scatter plot. We know that the variable major dep life is our depression variable, and it takes on the value 0 if the individual does not have major depression, and the value 1 if the individual does have major depression. Thus, we can plug in the values 0 and 1 into our major dep life variable to get the expected number of nicotine-dependent symptoms for each group.
As we can see, we would expect daily smokers without depression to have 2.19 nicotine-dependent symptoms, and daily smokers with depression to have 3.55 nicotine-dependent symptoms. Remember that we previously subset our data to daily smokers aged 18 to 25. Notice that this is also the mean number of nicotine-dependent symptoms for each group, which we can see by running summary statistics.
So although we may not be working with a best fit line, we are still generating important descriptive information out of this equation. Again, this does not mean that everyone in my sample with depression has exactly 3.5 symptoms. Obviously, no one can have half of a symptom. Our low R-squared value, 0.10, tells us that we're only capturing a small amount of the variability, 10%, in the number of nicotine-dependent symptoms among daily smokers. But nonetheless, this is the value that we would expect given our data. Also note that the categorical variable is a binary categorical variable. If your categorical variable has more than 2 levels, you will need to create dummy variables for your analysis. We'll go over this process in supplementary material. There are a lot of factors that contribute to internet use rate and nicotine dependence, the response variables in each of my examples. If we had more information, and if we included those other factors in our model, it is quite possible that our expected values would be even closer to our observed values. We could include several explanatory and/or predictor variables into our model in order to evaluate both the independent contribution of multiple explanatory variables in predicting our response variable, and also in order to evaluate whether specific variables confound the relationship between our explanatory variable of interest and our response variable.
While we now have evidence that depression is significantly associated with the number of nicotine-dependent symptoms endorsed by young daily adult smokers, our sample, another likely predictor of nicotine-dependent symptoms is, of course, the number of cigarettes a person smokes each day.
What if number of cigarettes is associated with both our explanatory variable, major depression, and response variable, nicotine-dependent symptoms? What if it is really smoking rather than major depression that is associated with number of nicotine-dependent symptoms?
To evaluate whether this is true, I add number of cigarettes smoked per day to my model. Proc GLM, model, ND symptoms equal to major dep life, number cigs smoked, / solution, Here's the output. We examine the p-values and parameter estimates for each predictor variable, that is, our explanatory variable, depression, and our potential confounder, number of cigarettes smoked. As you can see, both p-values are less than 0.05, and both of the parameter estimates are positive.
Thus, we can conclude that both major depression and number of cigarettes smoked are significantly associated with number of nicotine-dependent symptoms after partialing out the part of the association that can be accounted for by the other. In other words, Depression is positively associated with number of nicotine-dependent symptoms after controlling for number of cigarettes smoked, and number of cigarettes smoked is positively associated with number of nicotine-dependent symptoms after controlling for the presence or absence of depression. Note that if a parameter estimate is negative and the p-value is significant, it would mean that there was a negative relationship between that variable and the response variable.
Suppose we started with a different explanatory variable. Dysthymia is a pervasive, low-level depression that lasts a long time, often a few years. Suppose we wanted to test the linear relationship between dysthymia, a binary categorical explanatory variable, and number of nicotine-dependent symptoms, a quantitative response variable.
The code would be proc GLM semicolon model ND symptoms equal to dyslife / solution semicolon. You can see from the significant p-value and positive parameter estimate that dysthymia is positively associated with number of nicotine-dependent symptoms. That is, the presence of dysthymia is associated with a larger number of nicotine-dependent symptoms, and the absence of dysthymia is associated with a smaller number of nicotine-dependent symptoms. While dysthymia is long-lasting, low-level depression, major depression is a disorder characterized by a discrete episode of severe depression. So what happens when we control for major depression in this model? As you can see, dysthymia is no longer significantly associated with number of nicotine-dependent symptoms after controlling for major depression. Here we have an example of confounding. We would say that major depression confounds the relationship between dysthymia and number of nicotine-dependent symptoms because the p-value for dysthymia is no longer significant when major depression is included in the model. As in the previous example, using multiple regression, we can continue to add variables to this model in order to evaluate multiple predictors of our quantitative response variable, number of nicotine-dependent symptoms. Here we can see that when evaluating the independent association among several predictor variables and number of nicotine-dependent symptoms, major depression and number of cigarettes smoked are positively and significantly associated with number of nicotine-dependent symptoms, while dysthymia, age, and gender are not. Proc GLM semicolon model ND symptoms equal dyslife, major deplife, number cigs smoked, age, sex, / solution semicolon.
Multiple regression is the appropriate statistical tool when your response variable is quantitative. If your response variable is categorical with 2 levels, we need to use another multivariate tool, Logistic Regression.
The SAS command that we'll use is called proc logistic. Just like proc GLM, you type in your response variable, the equal sign, and then your explanatory variable followed by a semicolon. Our response variable, nicotine dep, is binary, yes or no to nicotine dependence, and so we should use a logistic regression. Note, however, that because our variable is coded 0 and 1, where 0 is the absence of nicotine dependence and 1 is the presence of nicotine dependence, we also need to add the word descending to the code to assure that we're predicting the presence of nicotine dependence rather than its absence. We also have an explanatory variable called soc/PD-life that indicates the presence or absence of social phobia, which is an anxiety disorder marked by a strong fear of being judged by others and of being embarrassed. Thus, our code would be proc logistic descending semicolon model nicotine dep equal to soc/PD-life semicolon. Let's take a look at the output here. Similar to the multiple regression output, we can see the number of observations and number of observations with complete data that were used in the model. Here we see the name of our response variable, nicotine dep. Also, similar to the multiple regression output, we see a table with the parameter estimates and the p-value. Notice also that our regression is significant at a p-value of 0.0002. Of course, using the parameter estimates, we could generate the linear equation nicotine dep is a function of 0.38 plus 1.23 times SOS PD life.
But let's really think about this equation some more. In a regression model, our response variable was quantitative, and so it could theoretically take on any value. In a logistic regression, our response variable only takes on the values 0 and 1. Therefore, if I tried to use this equation as a best fit line, I would run into some problems. Instead of talking in decimals, it may be more helpful for us to talk about how the probability of being nicotine dependent changes based on the presence or absence of social phobia. For example, are those with social phobia more or less likely to be nicotine dependent than those without social phobia? Instead of true expected values, we want probabilities.
Described visually, we'll no longer find the best fit line, shown in red, very helpful to us, as our outcome variable cannot take on any value. Instead, we're saying that there is somewhere along our x-axis where our outcome variable moves from being more likely to be a 0 to being more likely to be a 1. Our goal will be to quantify the probability of getting a 1 versus a 0 for a given value on our x-axis.
In order to better answer our research question, we will choose odds ratios as opposed to coefficients. The odds ratio is the probability of an event occurring in one group compared to the probability of an event occurring in another group. Odds ratios are always given in the form of odds and are not linear. Odds ratios are often a confusing topic for students when they're first introduced to it, so it will be important to go through it conceptually and better understand exactly what an odds ratio is and what it means.
An odds ratio can range from 0 to positive infinity and is centered around the value 1. If we ran our model and got an odds ratio of 1, it would mean that there's an equal probability of nicotine dependence among those with and without social phobia. Those with social phobia are equally as likely to be nicotine dependent as those without. It's also likely then that our model would be statistically non-significant. If an odds ratio is greater than 1, it means that the probability of becoming nicotine dependent increases among those with social phobia compared to those without. In contrast, if the odds ratio is below 1, it means that the probability of becoming nicotine dependent is lower among those with social phobia than among those without.
So how do we calculate the odds ratio? It is possible to do this by hand. The odds ratio is the natural exponentiation of our parameter estimate. However, we could also let SAS do this for us. As you can see, the odds ratio, or point estimate, and associated confidence interval are part of the SAS output for logistic regression. Because both my explanatory and response variables in this model are binary, coded 0 and 1, I can interpret this odds ratio in the following way. Those young adult daily smokers, my sample, with social phobia are 3.4 times more likely to have nicotine dependence than young adult smokers without social phobia.
We also get a confidence interval for our odds ratio. Remember that our data set is just a sample of a population. We don't have every young adult daily smoker in the U.S. This confidence interval from 1.85 to 6.97 tells us which values for the odds ratio parameter in the population are plausible. It tells us that we can be 95% confident that if we were to draw additional samples of young adult daily smokers in the U.S., 95% of the time, that is, in 95 out of 100 possible samples, the confidence interval calculated for each sample would contain the value of the odds ratio in the actual population.
It's important to keep in mind that the odds ratio is simply a statistic calculated for this sample. So looking at the confidence interval, we can get a better picture of how much this value would change for a different sample drawn from the population. Based on our model, those with social phobia are anywhere from 1.78 to 6.61 times more likely to have a nicotine dependence than those without social phobia. The odds ratio is a sample statistic, and the confidence intervals are an estimate of the population parameter.
But what happens when we control for major depression? As you can see, both social phobia and major depression are independently associated with the likelihood of having nicotine dependence. Given that both social phobia and major depression are positively associated with the likelihood of being nicotine dependent, and our predictor or explanatory variables are both binary, we can interpret the odds ratios in the following way. Young adult daily smokers, the sample population, with social phobia are 2.3 times more likely to have nicotine dependence than young adult daily smokers without social phobia after controlling for major depression. Also, daily smokers with major depression are 3.7 times more likely to have nicotine dependence than daily smokers without major depression after controlling for the presence of social phobia. Because the confidence intervals on our odds ratios overlap, we cannot say that major depression is more strongly associated with nicotine dependence than is social phobia. For the population of young adult daily smokers, we can say that those with social phobia are anywhere from 1.2 to 4.6 times more likely to have nicotine dependence than those without social phobia, and those with major depression are between 2.7 and 5.0 times more likely to have nicotine dependence than those without major depression. Both of these estimates are calculated after accounting for the alternate disorder. As with multiple regression, when using logistic regression, we can continue to add variables to our model in order to evaluate multiple predictors of our binary categorical response variable, presence or absence of nicotine-dependent symptoms. Another example of confounding occurs when a logistic regression model is run to test the association between panic disorder as the explanatory variable and nicotine dependence, the response variable. Panic disorder is an anxiety disorder characterized by recurring panic attacks. Here we see a significant association, and note that young adult daily smokers with panic disorders in our sample are 2.8 times more likely to have nicotine dependence than young adult daily smokers without panic disorder. However, when we add major depression to the model, panic disorder is no longer significantly associated with nicotine dependence. Here we have an example of confounding. We would say that major depression confounds the relationship between panic disorder and nicotine dependence because the p-value for panic disorder is no longer significant when major depression is included in the model. Further, because panic disorder is no longer associated with nicotine dependence, we wouldn't interpret the corresponding odds ratio, but would interpret the significant odds ratio between major depression and nicotine dependence. That is, that young adult smokers with major depression are 3.7 times more likely to have nicotine dependence than young adult smokers without major depression after controlling for panic disorder.
By now, you should be feeling a little more comfortable with the idea of generating a regression model when your outcome variable is binary. Remember to always code your outcome variable so a 0 means no outcome and a 1 means that an outcome occurred. Use the word descending following proc logistic. This is true whether your outcome is positive, such as graduating from college, or negative, such as developing nicotine dependence.